Hey everyone, welcome back to Trigonometry. This will be lecture 6 of the course, and in this section we're going to continue with our graphs of trig functions by, we discussed sine and cosine previously. Now we're going to move into the remaining functions, so tangent, cotangent, secant, and cosecant. So let's go ahead and get started. And we'll call this section 2.2, graphs of other trig functions. Okay, and so let's go ahead and start with the tangent function. So let's start with the graph of y equals tan x. Okay, so just like before, I want to start by plotting some points. So we'll have x and then tan x here. Okay, so let's plot some points. So 0, pi over 6, pi over 4, pi over 3, 5 pi over 12, 17 pi over 36, 89 pi over 180, and we'll say 1.57 pi, or radians, and then pi over 2. All right, so we're converging to pi over 2 here. And so if I just kind of, you can do this on your own, but I'll just tell you what the value of tangent is at each of these. So at the tangent of 0 is 0, right? The tangent of pi over 6 is 0.6, and then at pi over 4 it's 1, right? Because the sine and the cosine are both equal there, so the ratio would be 1. Pi over 3, the tangent is 1.7, and then 3.7, and then 11.4. And then, you know, we're getting closer and closer to pi over 2 here. And so at the tangent of 89 pi over 180 is 57.3. And then when we get even closer, it jumps up to 1255 approximately. And then we know that the tangent is undefined at pi over 2. Okay, so what in the world is going on with this trig function? What is it doing? Well, if you remember, the tangent is equal to the sine over the cosine. Okay, so as x increases towards the value of pi over 2, right, as x increases towards the value of pi over 2, the tangent is going to start to increase as well. And the closer you get to pi over 2, the faster it increases. Right, now, this is a pre-calculus course, but what we could say here is that the tangent of x goes to infinity. The value of this function goes to infinity as the value of x, the argument of the tangent of x, goes to pi over 2. Now, this is a little bit of calculus sort of concepts. Right, this is the idea of a limit that you don't encounter in trigonometry, not until you get to calculus. But the idea is that as we get closer and closer to pi over 2, the value of the tangent gets closer and closer to infinity. And it's in fact the case that we can't directly evaluate tangent of pi over 2 because the cosine is 0 at pi over 2. So you can think about it like this. When we're really, really close to pi over 2, then the sine, the numerator here, is really, really close to 1. And when we're really, really close to pi over 2, the denominator, the cosine, is really, really close to 0. So it's like this kind of, we'd get into arithmetic kind of like this, 0.999999999 divided by 0.000000001. If you take something like this and you plug it into a calculator, you see you get a pretty large number, right? And so this is very, very close to 1. This is very, very close to 0, right? And so that's why these numbers start to explode as you get closer and closer to pi over 2. So how does this translate when we get to the graph of the tangent? Well, what you end up with is basically what you would call asymptotes in sort of in like an algebra course, right? So this translates into vertical asymptotes. Okay, and so what the tangent function ends up looking like is very strange. Let me show you. I'll draw a picture of it here. Okay, so this is going to be our x-axis, and then we'll put the y-axis right in the middle. Okay, so you've got your x-axis and your y-axis. And I'm going to say pi over 2 is over here, and then we'll put negative pi over 2 here. So pi over 2 and negative pi over 2. Right, and at pi over 2, you're going to have a vertical asymptote. That means the graph of the function cannot cross this vertical line. Right, and what ends up happening with tangent is it starts at 0, as we see here. And as we start to move closer and closer to pi over 2, the value gets larger and larger. What that translates into is a shape kind of like this. Okay, and it turns out over here it does the exact same thing except in the other direction. Right, so this is kind of what the tangent looks like. And if that's not weird enough, it actually does this. So let's see, 1, 2, 3, this would be pi. And then 1, 2, 3, this would be 3 pi over 2. Okay, so it actually repeats this indefinitely on either side of the graph. And so you'd have another one over here. Right, and you have another one here. More asymptotes. Right, so this is the graph of tangent of x. This is the graph of y equals tan x. Okay, so very strange function, very strange graph, right? But this is what it looks like, and it should be intuitive, right? So we know that at all of these vertical asymptotes, that's where the cosine is equal to 0, right? And the sine is equal to 1. So 1 divided by 0, that's why you have undefined here, right? But if you go just off of these axes, you know, you're either going to have an extremely large positive number or extremely small negative number, right? And so that's where you get this kind of asymptotic behavior. So very different from the sine and cosine, which were functions bounded above by 1, bounded below by -1. Here the tangent has no upper bound at all, right? It heads to infinity, okay, and negative infinity. Okay, all right. And so let's talk about, are there any facts we should know about the tangent function? Let's see here. Yeah, so what's the period of the tangent function? Well, you can see just by looking at this that it repeats itself every pi, right? So this section here is exactly like this section, exactly like this section. So the period is pi. What's the domain? Well, all real numbers, right? You can see this is going to repeat itself indefinitely along the x-axis. So all real numbers except for these guys. You cannot plug these guys into the function, so it's all real numbers except for multiples of pi over 2. Okay, and what about the range? Well, the range is all real numbers. We can see that by looking at this. Right, here's, there's no real number that this is going to infinity. Right, so to get a really large number, all I have to do is get really, really close to a multiple of pi over 2. Okay, all right, and so that's kind of, an intro to the tangent function. Let's talk about how to practically graph this thing. Okay, how do we graph this guy? And so for this, we're going to use, we're going to kind of cut to the chase here. We're going to talk about how to graph y equals a times the tangent of bx minus c. Okay, and in this case, it's going to be for b greater than 0. Okay, so I'm going to outline a process for graphing the tangent function and variations of the tangent function. Okay. Okay, and it's going to be a little different than what we used for sine and cosine. Okay, so step 1 here, We're going to find two consecutive asymptotes by finding an interval containing a period. Okay, so let me write that down. Find two consecutive asymptotes by identifying an interval containing one period. And how will we do that? Okay, and so the way we're going to do that is we're going to start with the fact that tangent, the base function tangent, has a period between negative pi over 2 and pi over 2. Okay, now this is not the regular tangent function, so we have to do a little bit of work to this. And so we're going to take the bx minus c and put it in between here. Okay, and so this will by kind of using this as our starting point, we'll be able to figure out, like, okay, how does b and c shift and or change the period? Okay, and so in this case, we would say that, a pair of consecutive asymptotes occur at, basically bx minus c equals negative pi over 2 and bx minus c equals positive pi over 2. Okay, and we'll get into practically how this works when we get some real numbers in here, but I think you'll see this is a very straightforward process once you do an example or two. Okay, so just like with the sine and cosine, the b and the c are going to change the period of the they're going to change the period and of the tangent function, right? So they'll shrink it or stretch it. Okay, so that's step one. Step two is we want to identify an x-intercept somewhere between the two midway between the two asymptotes. So identify an x-intercept midway between the two asymptotes. Okay, right, so you're going to figure out what your asymptotes are here. So you'll have maybe negative pi over 2 here and then pi over 2 here, and then this step 2 is just what's the point that's right in the middle of those two values. That's easy enough to find. You just kind of add them together and divide by 2. Okay, and we'll do a concrete example in a second. I want to get the steps down first. Step 3, right, is just kind of like with the sine and cosine. We want to find the 1/4 and the 3/4 points. Okay, these points are going to be kind of special because they will have y coordinates of negative a and a, respectively. Right, so the 1/4 point will have a y coordinate of negative a, and the 3/4 point will have a y coordinate of a, right? A being this guy right here. And that's going to tell you something about how steep the curve of the tangent function is. And so flipping this over just for a moment, you can see there's a steepness here, right? Now, depending on where this falls, you can imagine it could look like this. It could also hug the x-axis more and go like that, or maybe it's even flatter like that, right? So depending on where this quarter point is, that's going to be the value of a, which you can read off of the function right here. Okay, that's very convenient. And then finally, step 4 is just to plot all these points and connect them. Okay, very simple. All right. Very simple, right? Well, let's do an example, and I think you'll see that it is actually fairly straightforward. Okay. Let's do this example. Let's say we want to graph y equals tangent of x plus pi over 4. Okay. So step 1, remember, is to find those consecutive asymptotes. So let me write that in just so we can make the connection here. Find two consecutive asymptotes. Now the way I said to do that was to use this. Negative pi over 2 is less than bx minus c, which is less than pi over 2, right? And so just kind of using that as your structure, let's plug in our values here. So negative pi over 2 is less than x plus pi over 4, which is less than pi over 2. Okay, and so what ends up happening here, we're going to have a left-hand asymptote at x plus pi over 4 equals negative pi over 2, right? And so we could just do the math here, and we could see that that means x is equal to negative pi over 2 minus pi over 4, right? Which of course is negative 3 pi over 4. Okay, and then the right-hand asymptote is going to be at x plus pi over 4 equals pi over 2, right? And so that means x is equal to pi over 2 minus pi over 4, right, which is pi over 4. Okay, so we've got our left-hand asymptote and our right-hand asymptote, and so that means our asymptotes are negative 3 pi over 4 and pi over 4. So it's shifted somewhat, isn't it? Right, normally this started out as negative pi over 2, now it's shifted down to negative 3 pi over 4, and this one is normally at pi over 2, and it's shifted down to pi over 4. Right, so it's kind of everything's shifted down by 1/4 of a pi. Right, and you can kind of see maybe that's intuitive given that you're adding pi over 4 to the argument. Okay, right, so that's step 1. So we've got these guys here. Now step 2 is to find the midway point. Identify the midway point between the asymptotes. Okay, so this is really easy to do. You can basically add them together and divide by 2. You just need the average of these two numbers. So negative 3 pi over 4 plus pi over 4 all divided by 2. And so this you get negative 2 pi over 4 over 2. And so what you end up with is negative, well, you can think of it like this, negative 2 pi over 4 times 1/2. And so this is negative pi over 4. So that's your midway point. And this is going to be where the x-intercept occurs. All right. And step 3 is going to be the identification of those 1/4 and 3/4 points. So let's actually draw this out now. So I've got my axis here, right? Let's say this is negative 3 pi over 4, and then we'll go up 3, 1, 2, 3, and we'll put the midpoint here, negative pi over 4, and then 1, 2, 3, get us to the positive pi over 4. Okay, so I've got my lower asymptote, my upper asymptote, and my midpoint. So I need to know what's here and here. Right, this is the 1/4 point, this is the 3/4 point. Well, I could just add these together and divide by 2 again, right? So I could say the 1/4 point is going to be equal to negative 3 pi over 4 plus negative pi over 4 over 2. Right? And if you do that math, you'll see that that's negative pi over 2. And the 3/4 point will be negative pi over 4 plus pi over 4 over 2, which is 0. So that's a 0, which you could just see by looking at it, I guess, midway between negative pi over 4 and pi over 4 must be 0. Right? And so this tells you everything you need to know. Right? So basically your graph is going to come down and go like this. Okay, so let's actually plot it nicely, though. Let's plot the thing nicely. That'd be step 4. Okay, so let's say I've got my negative 3 pi over 4 here. And then somewhere up here, I've got my pi over 4. And we'll say right in the middle is this, and that is going to be negative pi over 4. And then I've got 0 here, and I've got, what is this one? This one is negative pi over 2. Okay, and so I've got my, here's my y-axis here, actually, technically. But I've got vertical asymptotes along this guy here, and I've got vertical asymptotes along this guy here. Right? The graph goes through there. That's the x-axis. And what was the value of a for this example? Remember, the function was y equals tangent of x plus pi over 4. And so our value of a is 1. And so we just note that on the, maybe we'll call this 1, and we'll call, let's see, 1, 2, 3, 4. We'll call this negative 1. And so the graph is going to go through right here, and it's going to go through right there. So it looks a bit like this. Okay? So that's all you need to do. Right? Now remember, this is a here, and this is negative a. Okay. Okay, so there you go. That's the tangent. That is how we would go about graphing the tangent function. Okay, what about the cotangent? Okay, it's going to be very similar to the tangent, just a little, it varies in a couple of details. It has the same basic shape, though. What about the cotangent? Well, the cotangent looks real similar, right? But remember that the tangent is sine over cosine. Remember, so tan x is sine x over cos x, and the cotangent of x is cos x over sine x. Right, so the asymptotes are going to vary. So here you had asymptotes when cosine was 0, and here you instead have asymptotes when sine is 0. Also, the direction of the graph is going to vary as well. Okay, so this is your x-axis, and this is your y-axis. Then if I come over here to pi, I'm going to have an asymptote at 0 and at pi for cotangent. And so we could say this is negative pi. Right, so I have this kind of behavior here. Right, and so the cotangent looks a lot like the tangent, except where the asymptotes land is different. They land at multiples of pi now instead of multiples of pi over 2. And the orientation of the actual graph is different. So tangent started at the bottom and went up. Cotangent starts at the top and comes down. Okay, but otherwise they're exactly the same, and the way you treat them is exactly the same as well. Okay, so the period here is the same. It's pi. The domain is all real numbers, except for what? Multiples of pi. Okay, the range, all real numbers. Right, so it looks a lot like the tangent function, just a little bit different. And the way we deal with it is the same as well. Okay? The way we actually plot it is very similar. Right? So how does it vary? We're actually I'm gonna skip an example of this because I think it's so similar. The only place it varies is in step 1 when we find the 2 consecutive asymptotes. So instead, I'll just make a line down here. Okay, for cotangent, step 1 finds consecutive asymptotes using negative pi is less than bx minus c, which is less than pi. That's the only difference. Otherwise, it's exactly the same technique here. You start by finding the consecutive asymptotes. You identify the midpoint between the 2 asymptotes. You identify the 1/4 and 3/4 points between the midpoint and the asymptotes. And then you plot everything. Okay, and again, with the 1/4 and 3/4 point, a and negative a are going to be the y-coordinate. Right, so otherwise, exactly the same. Exactly the same. Okay, very good. Let's talk about cosecant and secant. Let's start with, so what about cosecant and secant? Right, so for these guys, what we need to keep in mind is that these guys are related to sine and cosine. Right, so recall that the cosecant of x is equal to 1 over the sine of x. Right, and the secant of x is equal to 1 over the cosine of x. Okay, so this tells us basically that the value, for example, the cosecant here, this tells us the value of the cosecant function is the reciprocal of the value of the sine function. Okay, and so here's what the cosecant function looks like. Let me draw you an example of it. This is the base y equals cosecant. So I've got my x-axis and I've got my y-axis here. And so when I draw the cosecant, what I want to do is I want to start by drawing the sine function. Right? So the sine function starts down here at 0. And let me put in some values. So we'll say that's positive pi over 2. And 1, 2, 3, we'll put negative pi over 2 here. Okay, and then 3 more will be pi, and then negative pi, and then 3 pi over 2, and negative 3 pi over 2, and negative 2 pi, and 2 pi. Okay, so we'll start with that. And so what does the sine function do over here? Well, and we'll put this as, we'll say this is 1, and this is negative 1. That'll work. So it starts down low, and then it goes up to here, and then it comes back down, and then it goes down to negative 1, and then it comes back to 0, and then of course, it continues on like this, right? It goes like this. Sine function. And it does the same thing over here, doesn't it? Okay, so this is the sine function. And so what the cosecant does is, well, look, wherever sine is 0, so namely here and here and here, whenever sine is 0, what happens to the cosecant? Well, if sine is 0, then you've got an undefined cosecant. So that means you've got vertical asymptotes here. And you got another one here, and you got another one here. Right, and then technically you got another one here and out here. I'll just put them all in just so we can see the pattern. Okay, so you got these vertical asymptotes everywhere where the sine function is 0 because you can't divide by 0. Right, so you can see those. And everywhere else, the cosecant is the inverse of the secant. So what ends up happening is it comes down and it touches the sine function, and then it goes back up. But over here it comes up to the sine function, and then it goes back down. And over here it does the same thing. Right? So it goes like this. Okay? And so this guy here, which I'm putting this like heavier line on, that's the sine function. That's not part of the cosecant function. It's just what we use to guide, as a guide to drawing the cosecant function. The cosecant function is this guy. Comes down, comes up, comes down, comes up, comes down. That's the cosecant function. So really, to plot the cosecant function, all you have to do is plot the sine function. Okay, you just plot the underlying sine function. Okay, and we'll get to that in a second. We'll do an example of that, but let's talk through all the characteristics of cosecant. Right. So what about the period? How often does this thing repeat itself? Well, you can see it repeats itself from 0 to pi. Well, so it's got some behavior here, and it's got a different behavior here, and then it starts to repeat itself. So actually the period here, it runs from 0 up to 2 pi. So the period of the cosecant is 2 pi. Okay, what about the domain? The domain is all real numbers except multiples of pi. Okay, all real numbers except multiples of pi. And the range, of course, is what? Well, the range is interesting here, right? Because see, notice here it comes down to 1 and then goes back up. And then over here it comes up to -1 and then goes back down. So there's this band right in the middle that the cosecant can never be equal to. Right, so it's all, the range there is therefore is all real numbers except for numbers in this band. Okay, so we could say all real numbers except for values of x, of y here, of y less than or equal to -1, or y, all real numbers except for values of y, oh my goodness, between 1 and -1. That's the way to say it. Okay, right, so y can never be between 1 and -1. Because that's the value of the sine function. Cosecant is always the reciprocal of that, so it's outside of that. Okay. All right. Very good. And while we're on the topic, before we move into how to graph variations of this, what about secant? Secant's going to borrow the same idea, except the underlying function in the case of secant will be the cosine. So let's draw a picture of what the secant function looks like. Okay, so again we'll start with our blank axis here. 1, 2, let's see, 1, 2. Okay, and we'll just go 1 and -1, and we'll make this pi over 2. 3 pi over 2 pi. Oh, actually, shoot. I want to make this pi and then 3 pi over 2. Sorry about that. And then 2 pi. There we go. And then we'll make this negative pi over 2 and negative pi, negative 3 pi over 2 and negative 2 pi. Sorry about that typo there. This is pi, 3 pi over 2. Okay, so what does the cosine do? Well, you remember the cosine starts up here, and then it comes down, and it hits a minimum, and then it starts to come back up. Right, so it kind of looks like this. And it does the same thing over here. Right, Right, so it looks like that. That's the cosine function. So the secant is the inverse of the cosine. So everywhere cosine is 0, you're going to have an asymptote. Right, and then the secant is just going to, I'll put it in blue here, it's going to come down like that. It's going to come up like that. It's going to come down like that. That's the secant. So real similar to the cosecant. Obviously, you can see if you look here. So it's shifted, right? So the cosecant is up here, whereas, you know, on the secant that would cross an asymptote, right? So it's all shifted a little bit. Okay, but this is what the secant looks like. Okay, and so all of the same properties hold for the cosecant, or sorry, for the secant as before. Period is 2 pi. The domain is all real numbers, except for, in this case, it's multiples of pi over 2 instead of pi, right? Because here's the cosine is 0 here and here. And the range is going to, again, be all real numbers, except for the real numbers in that band right there. Okay, perfect. Perfect. Let's do an example of how to graph. Let's talk through how to graph a variation on these two. Okay, so graphing variations. Okay, so how do we want to do this? Well, basically, I mean, as you can imagine, really what you need to do here is you just need to graph the underlying functions, right? So to graph something like y equals -3 secant of x over 2, for example, we would use the graph of y equals -3 cosine of x over 2. Right, so we would use this as a template, and then we can draw in where the secant is going to lie relative to this. Okay. All right, let's do, you know, and so that's, you know, and it works the same way with the cosecant and the sine, right? To graph y equals 1/2 cosecant of x minus pi over 2, we just use the graph of y equals 1/2 sine of x minus pi over 2, right? Right, so this graph here will inform you about what that one looks like, and this graph here will inform you of what that one looks like. Okay, so let's take a look at an example here. Let's do an example. Okay, and this will give us an opportunity to kind of review what we talked about last time with the graphing of sine and cosine. So let's graph y equals -3 secant of x over 2. Okay, and just let's limit the domain here. So for x between -pi and 5 pi. Oops. Okay, so we're going to just kind of do this one side of it here. Okay, so let's see what this looks like. And so what we want to begin by graphing the cosine function, right? So y equals -3 cosine of, and I'm going to write it differently, 1/2 x. Okay, and so if we remember how to graph cosine, we got to start by identifying the amplitude, period, and phase shift. And so step 1 is to identify the amplitude, period, and phase shift. So the amplitude is 3, right? So that's the A on the front there. The period, how do we find the period? Well, remember the period is equal to 2 pi over b, right? So in this case, you've got 2 pi, and b in this case is 1/2. And so 2 pi over 1/2, if you do the arithmetic there, you can see that that's 4 pi. Okay, so this is going to extend the cycle, make the cycle longer. Okay, and this is going to stretch the sine function out, so it's going to have taller, it's going to be a taller wave. Right, and then there's no phase shift component because c is equal to 0. Okay, so what the phase shift would be c over b, and in this case you've got 0 over 1/2 or 0. So there's no shift in the phase. Okay. All right, and so we can start with identifying the 5 key points. Let me flip the page here. The next thing to do would be to identify the 5 key points. Okay, so that would be your x1, x2, x3, x4, x5. And since the phase doesn't vary here, we can just start the cycle at 0. Okay, and what do we know that the period is 4 pi, so we're going to add 4 pi over 4 to each of these. So this would be 0 plus 4 pi over 4, so 4 pi over 4 equals pi, right? And then this is going to be pi plus 4 pi over 4. Oh, each time I'm sorry, I guess I'm adding pi to this. So 2 pi. I probably should have caught on to that one quicker. Right, and then this one is naturally going to be 3 pi, and this one is going to be 4 pi. Right, so your 5 key numbers are nice and simple: 0, pi, 2 pi, 3 pi, 4 pi. All right. Okie dokie. And so now we need the corresponding y values. So y1, y2, y3, y4, and y5. And so, I mean, these can each be found by just evaluating the function, right? And so we would say y1 is equal to -3 cosine of x1 over 2, right? x1 is 0, so this is just going to be basically 1 times -3, so -3. Right, and this one will be -3 times cosine of x2, which is pi. Right, and so this is going to be 0. And this will be -3 times the cosine of 2 pi over 2, which would be just pi. And so here you're going to get a 1, which times, or sorry, -1 times 3. -3 is a +3. And then here you can see, you can kind of do the same exercise, and you get a 0, and you do the same exercise here, and you get -3. So the 5 points are, and you can write them out like this if you want: 0, -3, pi, 0, 2 pi, 3, 3 pi, 0, and 4 pi, -3. Okay, and we can just plot these now. Okay, so I'm going to put my -pi here, and then 1, 2, 3, 4. We'll make this my y-axis. And then 1, 2, 3, 4. We'll put a pi there. 1, 2, 3, 4. We'll put 2 pi there. And 1, 2, 3, 4. And 3 pi and 4 pi. Sorry, I'm off the screen here. There we go. Okay, and so we'll have an asymptote here, and we'll have an asymptote here, and at 3 pi we're going to have an asymptote, and then we'll also have one at 5 pi, won't we? Okay. All right, and so what that means then is our cosine is just going to be kind of laid in here. Right, now the one of the things to note, well, you don't want to just blindly draw this, but you can look here and you can see that at 0 you've got a -3. So 1, 2, 3. I'll do it like this. And so it starts here, and then it comes up, and then it tops out up here, and then it comes back down, and then it goes down again to here, and then back up. Right, so it kind of looks like this. So there's your cosine, and now what's the secant doing? Well, the secant is just going to mirror the cosine in these intervals. So it's going to come up like this, and then it's going to come down like this, and then it's going to come up like this. Okay, and so this is the cosecant function. And so y equals, what was it? -3. Sorry, this is -3 secant of x over 2 is this guy here in the blue. Okay, so that's how we would go about plotting the secant function. Okay, very good, very good. Okay, and so I think I'll probably end with that example. The cosecant is going to follow the same basic structure. You plot for cosecant, you start by plotting sine, and then the cosecant is going to fall in all of those intervals above or below the sine function, just like the secant here falls above or below the cosine function. Okay, all right. I think we'll leave it there, and when we come back next time, we'll start talking about the inverse trig functions. So this is kind of going to end our graphing of trig functions, but we'll pick up kind of more visual, another kind of visual section with the inverse trig function section next. So until then, take care.